Rasa community, welcome to the reading group. I'm Rachel. My levels are a little weird. Let me adjust. There we go. I'm Rachel. I'm a little bit tired, so we'll see how the reading group goes today. Slightly towards center. Today, we are reading the paper, right for the wrong reasons, Diagnosing Syntactic Heuristic in Natural Language Inference by R. Thomas McCoy, Ellie Pavlick, and Tal Linzen. That's no good. Let's make sure that we are actually muted so that we don't get a nasty, nasty echo. The paper is from, let me just check, ACL 2019, so a little while ago, and was it this one? I don't remember exactly why I know why I decided to read this paper. I don't remember if this is a paper that came up in the last reading group as a citation and I looked it up, or if it was one that I was talking about with some of the folks on the research group in Rasa. But let's read the abstract and then we can talk a little bit more about why I think this is particularly useful and interesting and good to know. Let me zoom in a little bit so we can actually read the text. How's that? A machine learning system can score well on a given test set by relying on heuristics that are effective for frequent example types but break down in more challenging cases. We study this issue within Natural Language Inference, NLI, the task of determining whether one sentence entails another. We hypothesize that statistical NLI models may adopt three fallible syntactic heuristics: the lexical overlap heuristic, the subsequence heuristic. Sorry, I wanted to read that as subsequent, but like with a C at the end, which is that's not the word, subsequence heuristic, and the constituent heuristic. To determine whether models have adopted these heuristics, we introduce a controlled evaluation set called HANS, Heuristic Analysis for NLI Systems, which contains many examples where the heuristics fail. We find that models trained on MNLI, including BERT, a state-of-the-art model, perform very poorly on HANS, suggesting that they have indeed adopted these heuristics. We conclude that there is substantial room for improvement in NLI systems and that Hans dataset can motivate and measure progress in the area. So, NLI is not usually part of a, certainly not part of a usual Rasa assistant. It's not really a core part of task-oriented dialogue systems, but these particular heuristics are things that will come up a lot when you are building assistants. So the three things that they talk about, so these are signals. These are being treated as signals by the system. Hi, Amina, good to see you. So these are being treated as signals by the system, right? So these are things that a machine learning system is like, yes, this is how I know that this is the case. When in reality, they're more like noise. So these systems are picking up on these particular patterns of language use and using those patterns to identify, categories, or in this case, whether or not something entails something else or not. And the problem with that is that it's not a coincidence that these things occur together, right? There is some signal there, but these systems have learned to over-rely on these cues. So something that we've sort of been, I've talked about quite a bit with folks at the Rasa research group is the degree to which a lot of, modern transformer models are really more like bag of words models, right? So things like token frequency is going to be really important. And these particular things, so lexical overlap, this is a big one for Rasa assistants when you're providing your training data. The degree of lexical overlap can absolutely, shift your system's answers. Subsequence heuristic, which I'm guessing is like matching subsequences, but we'll learn more about that. And then the constituent heuristic, which, constituents are a concept from semantics. Nope. Syntax is where I'm most familiar with them from. So those are ways in which systems are wrong, and these authors have created a data set to specifically a data set that has specifically examples where a system that is relying on these strategies will be wrong more often, and it's specifically for natural language inference, which again, not a core part of most task-oriented dialogue systems, but something that, you know, all of these heuristics are super important for us and building intent classifiers, and even beyond intent classifiers, you know, thinking about end-to-end learning. Lexical overlap is going to play a large role in how your end-to-end learning systems go. Hey, Robbie. So let's get stuck in, as British people say. Neural networks excel at learning the statistical patterns in a training set and applying them to test cases drawn from the same distribution as the training examples. This strength can also be a weakness. Statistical learners, such as standard neural network architectures, are prone to adopting shallow heuristics that succeed for the majority of training examples. Oh, thank you. Robbie said my talk yesterday was good. I gave a talk at our user group in Salt Lake City about data science portfolios. The video of that should be up soon-ish, TM. Shallow heuristics that work for the majority of examples, but what they're not learning are the underlying generalizations that they are intended to capture. So an example of this could be, in a human setting, would be if you're a teacher and you're using a multiple choice test to test your students, and instead of learning the material that instead of learning the material the test is about, instead the students learn a lot about how you write multiple choice answers and use that to figure out the correct answers, rather than using an underlying understanding of the material to get the correct answers, right? So like trivial example, if you always have C as the right answer in all of your tests, your students will just learn to pick C rather than reading the question, understanding what it's asking of them, and then you know, using that to pick the correct answer. And if you then have a test where all of the answers are A, your students are all going to fail it because they expect the answer to be C, and that's how they've learned to take the tests, not to do the thing that you want them to do when they're taking the test, if that makes sense. So that's sort of a human-y example of this particular problem. If such heuristics often yield correct outputs, the loss function provides little incentive for the model to learn to generalize to more challenging cases as a human performing the task would. This issue has been documented across domains in artificial intelligence. In computer vision, for example, neural networks trained to recognize objects are mislabeled by contextual heuristics. A network that is able to recognize monkeys in a typical context with high accuracy may nevertheless label a monkey holding a guitar as a human, since in the training set, guitars tend to co-occur with humans, but not monkeys. Oh, a really good example of this, I believe from ImageNet, is a seatbelt. So there's a lot of pictures of humans wearing seatbelts, and if you like generate images of humans from ImageNet, sometimes you'll get seatbelts in them. Similar heuristics arise in visual question answering systems. The current paper addresses this issue in the domain of natural language inference. The task of determining whether a premise sentence entails, i.e. implies the truth of, a hypothesis sentence. So a good example of this would be like, if it is true that I have drunk 3 cups of coffee, it is also true that I have drunk 2 cups of coffee, right? So there's no way for me to drink 3 cups of coffee without also having drunk 2 cups of coffee. So having drunk 3 cups of coffee entails having drunk 2 cups of coffee, but not the other way around. I can drink 2 cups of coffee without having drunk 3 cups of coffee. Just example that I happen to have to hand. As in other domains, neural NLI models have been shown to learn shallow As in other domains, neural NLI models have been shown to learn shallow heuristics, in this case based on the presence of specific words. For example, a model may assume a label of contradiction to apply input containing the word not, since not often appears in the examples of contradiction in standard NLI training sets. Hi, Smakrio? Sorry if I'm saying that wrong. And Cigar, hello, welcome. And this is an example that I use all the time. I think there was another paper that I tend to use as my citation for this, and it's not one of these. I could be wrong about that. The focus of our work is on heuristics that are based on superficial syntactic properties. Sorry, just an aside here. I no longer maintain a very thorough citation database. When I was, more actively working as a researcher, I had a database of all the papers I'd read. I mean, also written, but there are not as many of those. All the papers I'd read and sort of the main points that I used to organize that. And if you are interested in working as a researcher or currently are one, I would highly recommend using that to organize the papers that you read. I am not writing literature reviews very often right now, so it's not a huge need for me. But if it is for you, organize early. The focus of our work on blah, 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 syntactic properties. Considering the following sentence pair, which has the target label entailment. Robbie says, without doing it, understanding is very difficult. Yeah, it does help to have some grounding of, really anything, if you're trying to learn it. Considering the following sentence pair, which has the target label entailment, the judge was paid by the actor paid the judge. An NLI system that labels this example correctly may do so not by reasoning about the meanings of these sentences, but rather by assuming that the premise entails any hypothesis whose words all appear in the premise, right? So the, actor, paid, the, and judge, right? All of the words in the hypothesis appear in the premise. Crucially, if the model is using this heuristic, it will predict entailment for to as well, even though the label is incorrect in this case. The actor was paid by the judge, and the actor paid the judge. So if we're using sort of semantic role labels, here the judge would be, I don't know, maybe the source? The judge is where the money is coming from, and the money is going to the actor. And here, the actor is where the money is coming from, and it's going to the judge. So these might both be true, but one does not entail the other, nor do they contradict. They're just sort of, there's no entailment relationship there. Whereas here, the actor is the source of the money and it's going to the judge. The actor is the source of the money and it's going to the judge. These have the same underlying semantic structure. Louis says, I see, I remember. Yeah, there's a sort of a teaching mnemonic. I see, I remember. No, I hear, I forget. I see, I remember. I do, I understand. That's the one. Yeah, I know you're up about. Louis? Sorry if I'm saying that wrong. Okay, we don't need to zoom out yet. We're still in the text. We introduced a new evaluation set called HANS, Heuristic Analysis for Analysis. Heuristic Analysis for NLI Systems, designed to diagnose the use of such fallible structural heuristics. We target 3 heuristics defined in Table 1. While these heuristics often yield correct labels, they are not valid inference strategies because they fail on many examples. We design our dataset around such examples so that models that employ these heuristics are guaranteed to fail on particular subsets of the dataset, rather than simply show lower overall accuracy. And I'm going to read this and I'm going to pop up and look at the table. We evaluate 4 popular NLI models, including BERT, a state-of-the-art model, this was in 2019, on the HANS dataset. All models perform substantially below chance on this dataset. That's no good. That is worse than random guessing, barely exceeding 0% accuracy in most cases. We conclude that their behavior is consistent with the hypothesis that they have adopted these heuristics. And it's always, with modern neural methods, it's a little bit difficult to say why a system made the guess that it did. A lot of people will use attention as a proxy for this, and it can provide information, but it's not going to tell you what actually caused a system to do a certain thing. And we read I'm pretty sure a while ago we read a paper that was like, why are you using attention when there's this other method right here that gives you those actual examples? And I don't remember who it was by. I remember reading it, and I don't remember what the method was. But it's hard to get the information out. Why did a system do this? So this sort of experiment where you have, a hypothesis that these systems are making these choices based on these inputs, and changing the inputs in such a way as to trick systems that, if they are relying on that, should not get it right, is a way to sort of empirically provide evidence that systems are using these strategies rather than sort of formally proving it. And yeah, it's sort of, if you've come from a more formal statistical background, it can be a little bit disconcerting that a lot of neural methods are very much, this sort of experimentation, guess and test, because there's not as much formal understanding of why it is that different systems do different things. So that's the point there that I'm trying to make, I guess. So here are the examples. Lexical overlap. Assume that a premise entails all hypotheses constructed from words in the premise. The doctor was paid by the actor. The doctor paid the actor. And this is incorrect. So a good example of this, right, would be in a chatbot system if you have, let's say, two intents, right? One of them is make a booking and the other one is cancel a booking. And you see a lot of overlap between them, right? And you see, let's say, all of the words except, cancel or not are shared. I'm trying to come up with a good example. Sorry. Let me think about it for a second. Okay, so if you have an example in your training data that's like, I want a ticket to Milan, right? And you're in the middle of a conversation and your system is maybe misunderstood and they're like, okay, booking a ticket to Milan. And the person's like, no, I don't want a ticket to Milan. If your system's just like, I want ticket to Milan, yep, all those words are there that I've seen in this category. So I'm pretty sure that they're trying to book a ticket to Milan and you're ignoring, or you're not giving a lot of weight to that don't in there, you will have a frustrated user. And this is, it's very common problem that I see people run into, or there will be one word, right, that occurred in the training data for one intent that doesn't have a strong relationship to that intent, but that your system picks up. So there was an example, I was talking about this with somebody somewhere, and it might have been about a customer, so I'm going to keep my example as vague as possible, but there was a system that someone was working on, and there was one word, it was something like, let's say letter opener, that occurred in one of their intents and none of the other ones. And whenever letter opener showed up, that phrase was identified as being in that intent, regardless of, other words in the phrase, because that one word was a very strong signal. So yes, this definitely happens with neural intent classification for sure. These other ones I think are going to be slightly less relevant for us, but I think it's really helpful to think about this and to get sort of input from slightly related tasks. Robbie says, neural networks look like a combination of linear and logistic regression. I would say that we have a much better principled understanding of regression than we do of neural networks, just sort of in general. So that's lexical overlap, just like number of words overlapping. Subsequence. Assume that a premise entails all of its contiguous subsequences. So these are in the training data, right? So, or in this case, in the pair of things, the actor dance is a sequence that shows up here. So therefore, that must be extracting that must be something that is also entailed. So the doctor near the actor danced. Here, the actor is not doing the dancing. It is the doctor that is close to the actor. So near the actor is, a phrase that is modifying doctor. And if we remove that, we'd get the doctor danced, if that makes sense. And then constituents assume that a premise entails all complete subtrees in its parse tree. So in this example, right, where I said near the actor is a phrase that modifies doctor, you can chunk sentences up into at least one phrase. And here we have, you know, if the artist slept, this is a phrase, the actor ran. So this is a phrase, this is a phrase, but it is not true that the artist slept, right? So the actor running is conditional on the artist sleeping. And this is, you know, this is something that is in the sentence, but it is not true independent of the sentence. And this doesn't entail this, if that makes sense. Hopefully this makes sense. This is very semantic-y. So, yeah, I think this is another thing that does tend to show up in training data for you know, intent classification as well. Is there like a complete overlap between subsequences within, you know, the thing that the user is saying and then the examples that you've provided? And if there is, and it's good, right? If you were good at guessing what people have said, or if you've been using a lot of user data and you've really, you know, have a good coverage of the sorts of things that users say to your system, this might not be a bad thing. But, you know, like the negation examples, that might actually be kind of a frustrating thing. So what are you going to do about that? Add more training data would be my answer. All right, contributions. This paper has 3 main contributions. First, we introduce the Hans dataset, an NLI evaluation set that tests specific hypotheses about invalid heuristics that NLI models are likely to learn. Excuse me. Second, we use this dataset to illuminate interpretable shortcomings in state-of-the-art models trained on MNLI. And this, I think, is a specific dataset. These shortcomings may arise from inappropriate model inductive biases, from insufficient signal provided by training datasets, or both. I'm trying to come up with a good way to explain this. Mistakes? Yeah, I'm just gonna call that like, because the model is making mistakes due to the way that it's making decisions. I don't know, hopefully that makes sense. Third, we show that these shortcomings can be made less severe by augmenting a model's training set with the types of examples present in Hans. So this is the thing that's going to be most relevant for us if you're getting these examples where like you got lexical overlap between 2 intents, and you're getting misclassification that way. How do you do it? Data augmentation, add more data. And I think it's, you know, very telling that the solution here is data augmentation and not, you know, adding a machine learning component to handle it. That could be something that you choose to do. In general, adding data is going to make your life easier in the long run and also make your system more robust. These results indicate that there is substantial room for improvement for current NLI models and datasets, and that Hans can serve as a tool for motivating and measuring progress in the area. And here is a repository with the data and code. All right, syntactic heuristics. Cigar says, the actor is acting every time. Yeah. We focus on 3 heuristics: the lexical overlap heuristic, the subsequence heuristic, and the constituent heuristic, all defined in table 3. And I will say, for intent classification, if you are not doing any sort of parsing, or parsing, depending on your preference for pronunciation there, a subsequence and a constituent are going to be, for your purposes, identical. The heuristics form a hierarchy. The constituent heuristic is a special case of the subsequence heuristic, which in turn is a special case of the lexical overlap heuristic. Table 2. Sorry, my dog kept me up last night. He was very wiggly. Table 2 in the next page gives examples where each heuristic succeeds and fails. There are 2 reasons why we expect these heuristics to be adopted by a statistical learner trained on the standard NLI dataset, such as SNLI or MNLI. And the paper that we read, not last time, but the time before last, about fixing NLU benchmarks, same Bowman. First, the MNLI training set contains far more examples that support the heuristics than examples that contradict them. So here are the data sets, and if you're just using lexical overlap, you're going to be right roughly 10 times as often as you're wrong. If you just use subsequences, you're going to be right 50 times as often. Listen, fast arithmetic has never been my strong suit. That's why I like computers. And if you assume that every constituent is in a sentence is entailed by that sentence, then you will be right far more often than you are wrong. And I will say, to some degree, I believe both these data sets are crowdsourced. So to some degree, this is a function of the data collection and preparation method, because if I have to write 59 entailing sentences in 20 minutes to get paid $5 so that I can have lunch, I'm going to write the simplest sentences that I can so that I can do them more quickly. Even the 261 contradicting cases in MNLI may not provide strong evidence against the heuristics. For example, 133 of these cases contain negation in the premise, but not the hypothesis. Instead of using these cues to overrule the lexical overlap heuristic, a model may account for them by learning to assume that the label is contradiction whenever there is negation in the premise, but not the hypothesis. Yeah, this is the citation I usually use, the McCoy and Linzen paper. Is this the same McCoy? It must be. It must be the same McCoy. So I don't care, contradicts, I care. This is not a contradiction, contradicts, this is a contradiction. So if your model's like, I'm just looking for negation in here, and if I find it, it's a contradiction, it would be right in both of these cases. Scroll. There are some examples in MNLI that contradict the heuristics in ways that are not easily explained by other heuristics. See Appendix A for examples. However, such cases are likely too rare to discourage a model from learning these heuristics. MNLI contains data from multiple genres, so we conjecture that the scarcity of contradicting examples is not just a property of one genre, but rather a general property of NLI data generated in the crowdsourcing approach used by MNLI. And yeah, like what I just said, it is harder to write these examples than it is to write simpler examples that just use contradiction. So it takes more time. Is heuristics an NLP term? What does it mean? Yeah. Define heuristics. Involving or serving as an aid to learning, discovery, or problem solving by experimental and especially trial and error methods. The study or practice of heuristic. Thank you. Very helpful. So it is something that a system is using to learn, I guess. I don't know. It's one of those things where, like, I would not say it, but if somebody says it to me, it's like I have enough context for it that I'm like, okay. Yeah. Hopefully that helps. Good question. Thank you. However, such cases are likely too rare to discourage a model from learning these heuristics. MNLI contain blah, 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 blah. We thus hypothesize that any crowdsourced NLI dataset will make our syntactic heuristics attractive to statistical learners without strong linguistic pliers. Statistical learner is like basically counting things rather than creating a model of the relationships between things. The second reason we might expect current NLI models to adopt these heuristics, and just to, as an aside, for folks who are working on chatbots, this means that if you are crowdsourcing, let's say, like from yourself or your team, and you're just trying to figure out a lot of different ways to say something, you're probably not going to be able to come up with all the different ways that your population of users will come up to say something. And as a result, if you over rely on that data where you're just sort of sitting down and coming up with data for your system to use to train, you are going to be more likely to create a system that over relies on these things like lexical overlap and under relies on, other things that might be more helpful for your target user population. The second reason we might expect current NLI models to adopt these heuristics is that their input representations may make them more susceptible to these heuristics. The lexical overlap heuristic disregards the order of words in the sentence and considers only their identity, so it is likely to be adopted by bag-of-words NLI models. The subsequent subsequence heuristic considers linearly adjacent chunks of words, so one might expect it to be adopted by standard RNNs, which process sentences in linear order. Finally, the constituent heuristic appeals to components of the parse tree, so one might expect it to see adopted by tree-based NLI models. Basically transformers or bag-of-words models. I know that there is a feature for sort of reconstituting sequence from the text. It's not weighted as highly as you might think based on sort of subsequent work on BERT and other transformer models. Just like an optimizer in TensorFlow. Yeah, I think that's a good comparison. All right, dataset construction. For each heuristic, we generate 5 templates for examples that support the heuristic and 5 templates for examples that contradict it. Below is one template for the subsequence heuristic. I don't know why this one is so hard for me. It just is. See Appendix B for a full list of templates. So the noun 1 preposition, the noun 2 verb contradicts the noun 2 verb. The lawyer by the actor ran contradicts the actor ran. So here it is the lawyer that is running and not the actor. Also, this is a, no, it's not a garden path. I was going to say this is a garden path sentence, but it's not, because you would need another verb in here between lawyer and by in order to make people misparse it the first time. Linguistics. We generated 1,000 examples for each template for a total of 10,000 examples per heuristic. I would not recommend this for a chatbot in particular. Again, that is a different task than NLI. Some heuristics are special cases of others, but we made sure that the examples for one heuristic did not also fall under more narrowly defined heuristic. That is, for lexical overlap cases, the hypothesis was not a subsequence or constituent of the premise. For subsequence cases, the hypothesis was not a constituent of the premise. Coffee. So the reason that they are generating the data is they are looking at a specific hypothesis for these specific models. Again, I wouldn't recommend this. Your generation schema is super unlikely to be able to create a good representation of what people who are using your assistant in practice are saying, because no one is as unpredictable as users, and language is infinitely generative and infinitely complex, and you're never going to guess all the things, and that's, I don't know, it's kind of nice. One advantage of generating examples from templates instead of, e.g., modifying naturally occurring examples is that we can ensure the plausibility of all generated sentences. For example, we do not generate cases such as the student read the book contradicts the book read the student, which could ostensibly be solved using a hypothesis plausibility heuristic. So here, books don't read, right? There's a syntactic construction that I think is common in the northeast of the United States where you could say something like, the book reads great. That is less common than other types of syntactic constructions where books do not read, books are read. To achieve this, we draw our core vocabulary from Enger et al. 2018, where every noun was a plausible subject of every verb, or a plausible object of every transitive verb. Transitive verbs are verbs that take objects. So like, So if you have something like I eat, right, that is not transitive because there's no object. I eat spinach. Spinach would be the object of the verb eat. Some verbs can optionally take objects. Some verbs need objects. And some verbs need multiple objects, right? So like put. I put the cat on the mantelpiece. Put requires both an object and a preposition. Like, you can't just say, I put the cat. You need to have some place upon which the cat was put. Down on the floor, or wherever you put the cat, on its cozy little bed. Linguistics. Some templates require expanding this core vocabulary. In these cases, we manually curate the additions to ensure plausibility. And I think we're actually going to skip the next little bit because I don't think it is super relevant to us as chatbot folks. Yeah, I think we're going to hop down to the discussion rather than going through all of these results and talk about the data set in more detail. You're free to. The link is in the YouTube. Hello, Devil Kira. Robbie says, understanding anything becomes difficult if you go super deep in the subject. Yeah, no, I'd agree. There's an expectation of shared knowledge, particularly in research papers, that most people don't have. Like, I wouldn't be able to pick up like a, I don't know, cellular biology paper and like read through it and be like, ah, yes, and I even remember, like, when I was an undergrad, one of our professors had us read research papers in one of our seminars, specifically on child language acquisition. So when children learn their first language, and at the time I got about 20% of it, and I went back and I reread one of those papers recently, and I was like, I understand all of this. I have leveled up in reading linguistics papers specifically, and unfortunately it doesn't transfer across domains. It doesn't mean I'm really good at reading biology papers, but that's okay. There's always more to learn. Look at the devil. Kira says, I'm a doctor. I am a doctor. Yeah. Discussion. So, hopping back in, they built their data set, they tested a bunch of systems, the systems did bad, I'm sure we can look at here, yeah. So, here, 50% would be chance, if you were just randomly guessing one or the other, and all of these systems are at floor, which you don't see very often. Though each heuristic is most closely related to one class of model, e.g. the constituent heuristic is related to tree-based models, which you might be using in your natural language understanding pipeline, but probably wouldn't be. All models failed on cases illustrating all three heuristics. The finding is unsurprising since these heuristics are closely related to each other, meaning that an NLI model may adopt all of them, even ones not specifically targeting that class of model. For example, the subsequence and constituents heuristics are special cases of the lexical overlap heuristic, so all models can fail on cases illustrating all heuristics because all models have access to individual words. Though the heuristics form a hierarchy, the hierarchy does not necessarily predict the performance of our models. For example, Bert performed worse on the subsequence heuristic than on the constituent heuristic, even though the constituent heuristic is a special case of the subsequence heuristic. Bert is a transformer model, and if you're using the default Rasa setup, you will also be using transformer models, so I think that's probably the most relevant one of these of this batch. Such behavior has two possible causes. First, it could be due to the specific cases we chose for each heuristic. The cases chosen for the subsequence heuristic may be inherently more challenging than the cases chosen for the constituent heuristic, even though the constituent heuristic as a whole is a subset of the sequent one. Yeah, I don't think this is super relevant. Here's a good question. Do the heuristics arise from the architecture or the training set? So, does the fact that a model can be fooled by overlap words, is that because you are using a transformer model or an RNN model, or is it because of the specific training set you're using? A doctor of coding. So my PhD is from a linguistics department, and it was in natural language processing. And the specific thing that I was working on was what's called computational sociolinguistics. So the way that your social identity changes the way you both use and perceive language, and then studying that using computational tools. So a big part of my dissertation was building a machine learning model that used social cues about speakers during part of the automatic speech recognition process to try and make human-like errors as opposed to unhuman-like errors. Yes, so not a doctor of computer science, no. So you need both the training and the architecture to make a model. The model's poor results on Hans could therefore arise from architectural limitations, from insufficient signal in the MNLI training set, or from both. The fact that SPIN did markedly better at the constituent and subsequence cases than eSIM and DA, these are all just types of models, even though the three models were trained on the same dataset, suggests that MNLI does contain some signal that can counteract the appeal of the syntactic heuristics tested by Hans. SPIN's structural inductive biases allow it to leverage this signal, but other models' biases do not. So the way that SPIN is deciding to make decisions let it use more syntactic information than these other models. Other sources of evidence suggest that the model's failure is due in large part to insufficient signal from the MNLI training set rather than the model's representational capacities alone. So the reason these models are failing in these specific ways, it is not that these architectures are incapable of learning these patterns, it is that they are not represented well enough in the training data set. The BERT model we used, BERT-based uncased, was found by Goldberg 2019 to achieve strong results in syntactic tasks such as subject-verb agreement prediction, a task that minimally requires a distinction between the subject and direct object of a sentence. So subject, like I eat spinach, the direct object would be spinach, the subject would be I. Despite this evidence that BERT has access to relevant syntactic information, its accuracy was 0% in the subject-object swap cases. The doctor saw the lawyer contradicts that the lawyer saw the doctor, or does not entail, sorry. We believe that it is unlikely that our fine-tuning step on MNLI, a much smaller corpus than the corpus BERT was trained on, substantially changed the model's representational capabilities. So, yeah, we did fine-tuning. We don't think it changed the model's ability to understand these relationships or, potential to encode and transfer those patterns. Even though the model most likely had access to information about subjects and objects then, MNLI did not make it clear how that information applies to inference. So the samples given for training for this specific task were not enough to help the model learn these differences. Supporting this conclusion, McCoy et al., presumably the same as the first author, found little evidence of compositional structure in the InferCent model, which was trained on SNLI, even though the same model type in RNN did learn clear compositional structure when trained on tasks that underscored the need for such structure. So basically, hey, a model with the same architecture or the same overall architecture was able to learn these patterns. It seems to be the training data that is causing problems. These results further suggest that the model's poor compositional behavior arises more because of the training set than because of the model architecture. So at the very top of the reading group, I was like, hey, if you're working on building your conversational assistant, you're going to get more benefit from adding more and more varied training data. I mean, ideally training data from your users. That's the gold standard. That's what you really, really want. Then from tweaking your model architecture, right, and changing your NLU pipeline, once you are successfully getting from, text to features that make sense for you and your target language and your domain, you are going to get the most improvement from changing your training data and not from tweaking your model architecture or adding additional ensemble learning sorts of things. Anyway, so that's my point there. And it's interesting because the sort of basically the chatbots that you're building with Rasa, if you're using our approach, you are providing both the training data and specifying the model. And I know that the appeal of machine learning engineering is that you get to play with models and you get to like do the fun machine learning stuff. But assuming that you want your system to work, you should really be spending more time on your training data. And I don't know how to sugarcoat that. That's just the way it is. And I think that this paper is a really good representation of why that's so important, because these, you know, enormously powerful models trained for a really long time were unable to generalize well to new cases because the training data was insufficiently varied and didn't represent the whole class of things that these models would see in, you know, application. I think this is very much a research paper on research models, but, you know, if you really did need an NLI system that, you know, worked good, it would be important that they were able to handle all of the types of data that they saw in the wild, if you were. Finally, our BERT-based model differed from the other models in that it was pre-trained on a massive amount of data on a masking task, so fill in the blank, and a next sentence classification task, followed by fine-tuning on MLLI, while the other models were only trained on MNLI. We therefore cannot rule out the possibility that BERT's comparative success at Hans was due to a greater amount of data it has encountered rather than any architectural features. So BERT did a little bit better, but it looks like that might have been because it just got more training input. Yeah, so then they're checking if the data set was too difficult. Basically, this is just like human evaluation. Could a human do the task? And I'm guessing yes. Although mechanical Turk annotators found Hans to be harder overall than MNLI, their accuracy was similar whether the correct answer was entailment, 75%, or non-entailment. The contrast between the balance in the human errors across labels and the stark imbalance in the model's errors indicates that human errors are unlikely to be driven by heuristics targeted in the current work. So here you can see up above, the non-entailed was sort of at 0 and well below chance, and all of the human raters are well above chance for all of these different heuristics. I don't know what DA is here. So it is clear that these models are not working on data examples that are specifically designed to target these heuristics. What's the solution? What is causing the problem? Well, it's probably not the model architecture. These models with the same architecture and other training data sets are capable of learning the difference. The difference is the data, and the data, by updating the data and by adding specifically examples that are counter examples to the ones that So these models are really relying on overlap in tokens. If you provide specific examples where the overlap in the specific tokens is not what's going to help them, you know, classify things in the same, this isn't classification. I am conflating this task NLI with intent classification because it's a thing that's more relevant to y'all. But if I provide counter examples, right? So in this, you know, this where all the tokens are in the entail are in the second, does not entail this, even though there's a lot of overlap, right? Or examples in your intent classification, hey, I've got two intents that are very different and should be different intents, right? So like canceling a booking versus making a booking. If you have those intents, and let's say all of your canceling a booking have examples from trips within Europe, and all of your making a booking have examples from trips, you know, outside of Europe, just as an example, your system may learn, oh, I should look for lexical items that are about Europe because those only show up in the making a trip and not the canceling a trip. I might have done that backwards. Anyway, and if you provide those counterexamples in both your data sets, you're likely to get much better results, right? So that's sort of the intent classification version of this. So let's see how they augment their training data. The failure of the models we tested raises the questions of what it would take to do well on Hans. One possibility is that a different type of model would perform better. For example, a model based on hand-coded rules might handle Hans well. This is, for years and years, this was how NLP was done, just sort of generally as a field, before my time. But also sometimes still very helpful. A couple hand-coded rules can really help your system handle edge cases. However, since most models we tested are in theory capable of handling Hans's examples, but fail to do so when trained on MNLI, it is likely that performance could also be improved by training the same architectures on a dataset in which those heuristics are less successful. So basically taking the exact same model architecture, training on a new dataset where the dataset has counterexamples for these common uses of heuristics so that the system doesn't learn that those are what it should pay attention to. So going back to my example of like the teacher that always uses C as the answer, if instead the teacher like randomly sorts the answers, right? So some of them are C and some of them are A and some of them are B and some of them are D, then students won't learn that the way to take the test is to always guess C. They'll have to use some other strategy to take the test, if that makes sense. Whew. To test this hypothesis, we retrained each model on the MNLI training set augmented with a dataset structured exactly like Hans, but containing no specific examples that appeared in Hans. Our additions comprised 30,000 examples, and these were generated, roughly 8% of the size of the original MNLI dataset. In general, the models trained on the augmented MNLI performed very well on Hans. The one exception was the DA model, performed poorly on subcases for which the bag of words representation was inadequate. This experiment is only an initial exploration and leaves open many questions about the conditions under which a model will successfully avoid a heuristic. For example, how many contradicting examples are required? At the same time, these results do suggest that to prevent a model from learning a heuristic, one viable approach is to use a training set that does not support this heuristic. So this means that not only do the individual training examples matter quite a bit, but the relationship between your training examples also matters quite a bit. Pew, pew, pew. All right, and then other various things. So here is the model trained on, so here's the model trained on Hans with, the MNLI plus the examples that were like Hans, but not in Hans, on the Hans dataset. And as you can see, much better across the board, except for this particular DA model. And I don't know what that is. Not, I think, as super relevant for us. Transfer across subcases, and I think this is going to be not, again, super relevant for us. I don't think we're going to spend a second day on this paper, so I want to make sure that we get out all the things that are relevant to us from it. So transfer from an other data set, lexical overlap. Let's actually zoom out quite a bit. Yeah. So let's check out, I think, the related work section. I don't like the thing where the related work is at the end, but I understand it. I think medical papers tend to do this. They tend to have the related work at the end. This project relates to an extensive body of research on exposing and understanding weaknesses in models' learned behavior and representations. In the NLI literature, Pavlick, sorry if I'm saying that wrong, and Gururangan, I don't know what those vowels are supposed to be. Again, I'm sorry if I'm saying that wrong. So that due to biases in NLI datasets, it is possible to achieve far better than chance accuracy on those datasets by only looking at the hypotheses. Other recent work addressed possible ways in which NLI models might use fallible heuristics, focusing on semantic phenomena such as lexical inferences or quantifiers or biases based on specific words. All right, so these are all the ways in which, by your construction of your data set, you actually accidentally cause your model to cheat, right? Or not to cheat, but to learn that noise is a pattern that it should pay attention to in a way that's going to cause problems for you down the line. Our work focuses on structural phenomena following the proof of concept work done by Dasgupta et al. Our focus on using NLI to address how models capture structure follows some older work about using NLI for the evaluation of parsers. Rimmel and Clark, Medad et al. 2010. NLI has been used to investigate many other types of linguistic information besides syntactic structure. Outside NLI, many projects have used classification tasks to understand what linguistic and/or structural information is present in vector encodings of sentences. This was super. These papers were very recent when I was in grad school. I remember a lot of discussion around these. We instead chose the behavioral approach of using task performance on critical cases. I quite like that, actually. I like this paradigm, especially given the sort of general struggle with deep learning that we don't have. Oh no, the purple's been touching this whole time. Let me get that a little bit more centered. It's the first time I looked over there. Well, I really quite like this general approach given the limitations that we have in a theoretical understanding of the mechanisms of neural networks and deep learning. Unlike the classification approach, this approach is agnostic to model structure. Our dataset could be used to evaluate a symbolic NLI system just as easily as a neural one, whereas typical classification approaches only work for models with vector representations, period. Yeah, so they're saying, hey, this particular approach of looking at, not just individual words, but also collections of words and their relationships to each other within the sentence, and evaluating it using a data set that is designed to basically pick out those edge cases, should help. Similar to our, have you ever worked on DA, eSIM, etc.? Oh, these other, NLI systems? No, I've never actually worked on NLI. It's something that I know about. Like I have had, graduate level classes in formal semantics, and I'm sort of familiar with the NLP literature and semantics. But no, I have not worked with any of these other models. I worked with BERT, but I'm not familiar with these other models. They are presumably specifically natural language inference models. Where was I? Excuse me. All right. We were right in here, as I remember. So we also, other people looked at lexical overlap heuristics and NLI models for specific phenomena where word order matters. We generally treat word order like it doesn't matter in intent classification, just sort of generally. You can definitely take a more sort of structured parsing approach, but it's not the approach we take at Rasa. I think it'll probably be a little bit slower, and I think it'll be better suited for languages that aren't English, to be perfectly honest. We use a larger set of phenomena to study a more general notion of lexical overlap that is less dependent on the properties of a single phenomena, such as passives. So passive would be like the actor paid the judge, the actor was paid by the judge, where the subject of the sentence is not the agent of the sentence. Naik. Again, do not know what that vowel is supposed to be, my apologies. Et al. Also find evidence that NLI models use lexical overlap heuristics, but our approach is substantially different from theirs. This work builds on our pilot study in McCoy and Linzen 2019, same two authors, which study one of the subcases of the subsequence heuristic. Several of our subsequence subcases are inspired by psycholinguistics research examples. Sorry, that's hard to read. These works have aims similar to ours, but are concerned with the representations used by humans rather than neural networks. I would also say I genuinely appreciate that the authors did not suggest that they were building a cognitive model, because cognitive modeling is a separate thing. And just because your model has neural in the name does not mean that you have built a cognitive model. Modeling cognition was also one of the things that I was interested in graduate school. Finally, all of our constituent heuristic subcases depend on the implicational behavior of specific words. Several past works have studied such behavior for verbs. He knows it is raining entails it is raining, while he believes it is raining does not. So in English, you wouldn't code this in verbs, but in other languages, like I know Mongolian has an evidential case where the information about how certain someone is that something is occurring is encoded in the case system. And other languages do as well. It's just Mongolian is the one I happen to know off the top of my head. We extend that approach by including other types of words with specific implicational behavior, namely conjunctions, not conjectures, conjunctions and or prepositions that take clausal arguments, if, because. So these have to be, the assumption is that these are going to be followed by like basically like a little mini sentence. If you say just like because without a clause, or, you know, because cats or something, that's sort of playful and contradicts the expectations of what you should put after because. And adverbs, definitely, supposedly. McCartney and Manning also discuss the implicational behavior of these various types of words within NLI. Yeah, so we'll read the section on generalization, and then I'm going to say the same thing I've said like 5 times because I think it's so important. Our work suggests that test sets drawn from the same distribution as the training set may be inadequate for assessing whether a model has learned to perform the intended task. Instead, it is also necessary to evaluate on a generalization set that departs from the training distribution. So, I mean, in a Rasa context, that's conversation-driven development. The set that departs from the generalization in the training distribution will be your users, right? So your first pass is, if you're lucky, it's going to be with user data. But even if it is with user data, it's probably not going to be exactly the same domain, exactly the same sort of situation where people are talking back and forth. McCoy et al. Found a similar result for the task of question formation. Different architectures that all succeeded on the test set failed in the generalization set in different ways, showing that the test set alone was not sufficient to determine what the models had learned. This effect can arise not just from different architectures, but also from different initializations of the same architecture. So, big points from here. Transformer models in particular, so BERT is a transformer model in this case, care a lot about lexical overlap when learning to categorize things. That is super relevant for conversational systems, for dialogue systems, and for intent classification in general. So what do you do about it when your system has learned that specific words mean specific intents when that is not helping you in your deployed system? Add more training data. Add more training data that will get at the specific things that your system is over-relying on, so the specific tokens that someone is over-relying on. Just sort of more practically, what do I recommend? I would recommend, if you have normative frequency data, token level frequency data for your target language. So for a large corpus, you basically count how often certain tokens occur, and then compare that to your per class data, right? Your training data for your intent classification, and notice if any token that is not obviously related to the semantic content of the intent is overwhelmingly represented. So like the example where, you know, what was my example word? It wasn't fan boat, but I'm going to say it was fan boat. So if you only have fan boat occurring once in like the, I don't know, 400 words worth of training data, and it occurs, you know, once in, you know, I don't know, 400 million words. Fan boat is not a very common word. It's one of those boats that has the huge fan on the back. They get used a lot in the Everglades. I don't know why that's the word I came up with, but it is. Then, hey, fan boat is this word that's like super infrequent in your overall, maybe the corpus that your embeddings were trained on. It's super frequent in this category, even though it only occurs once. How are we going to, make sure that your system knows that fan boats occurs in other contexts as well, if that makes sense. So, basically, if you're at the point where your system is misclassifying things based on lexical overlap, change your training data and don't start by modifying your architecture, because most architectures are capable of learning the difference if provided with sufficiently informative training data that doesn't rely on these lexical overlap heuristics. That would be my general recommendation for people working on dialogue systems and specifically on intent classification. But I think even moving away from intent classification and towards more end-to-end learning, the specific content of the utterances becomes more and more important. All right, so that was the paper. I know we skipped a bunch. If y'all are particularly interested in natural language inference, I recommend to go back and read it. I think it was very relevant and interesting. Period. I don't know why I didn't put my prosody in a sentence ending way there. Yeah, so that's the paper. We will be back tomorrow with live coding, and we'll be working on, that SQL bug. I wonder what's up with the database. We'll find out tomorrow what's up with the database, and we'll try and fix it. Also, if you have not already signed up for L3AI, I would recommend checking it out. So it's, I don't think you can see the URL here, but it's l3-ai.dev, D-E-V. It'll be on June 17th. It's online. It's free. We'd love to have you there. There's going to be a bunch of great speakers. I'm going to be a speaker. And I think I'm going to talk about like anti-patterns, like common mistakes I see people make when they're starting to build, Rasa assistants and how you can avoid them. So that should be really good. And we have so many cool speakers. Alex and Ellen are going to be talking. Akila's going to be talking. She was on Office Hours a while ago. Akila's fantastic. Everybody's fantastic. Heather Nolis is going to be giving a talk. Heather's amazing. She's such a good engineer. Yeah, so Greg from Salesforce, really, he also has a linguistics degree, actually really knows what he's talking about when it comes to conversational design. So yeah, it should be a good time. We'd love to have you. Please sign up. And yeah, otherwise, I will see you tomorrow for live coding. I hope you enjoyed the paper, and I will talk to y'all tomorrow. Bye.